All right. Hello, everyone. Welcome to the 10th lecture. This one is on distributed database consistency, which is a pretty interesting topic, I think. Last time we introduced NoSQL databases, and there we basically showed how with a relational database using sharding, we were able to get higher write capacity by horizontally scaling the reads, but writes had to be sent to every node because every data node had a copy of all the data, and that fundamentally was the problem with scaling relational databases. Sharding was the approach to make that more scalable, but with NoSQL databases, we generalized the sharding problem to work with arbitrary data, and we did that by simplifying the data model to a key value store. By doing that, significantly limits the flexibility of the database, but it makes it very easy to distribute data because we can just take the key for each value and hash it to determine where which of the different nodes we should store the data on. So it's basically hash-based sharding on the key with one table is what NoSQL databases give you at a high level. I mean, in general, there are a lot of different NoSQL databases, and we'll talk about the differences in the next lecture, I think. But we're starting off with a very basic view of a distributed hash table NoSQL database. So this is a database like DynamoDB or Google's Big Table or Apache Cassandra. Those are all have a very simple key value type abstraction with some subtleties. Yeah, and it's very easy to build that kind of a system. As we saw last time with a distributed hash table, we break up the hash range into chunks, and those chunks should be of equal size, and we assign each node one of these chunks of the hash range, and then when we hash our key, we store it in the node that corresponds to the range that the hash fell into, right? And so that'll be the same every time a client hashes that key, so it'll always go to the right place, and it doesn't have to ask any one central location, where do I find this data? That's really what makes it scalable. The clients can just immediately go to the right place to find their data, which is similar to the sort of DNS-based load balancing approach on the front end. That's kind of an analogy. As long as the clients know what these nodes are, how to reach them, what their IP addresses are, in other words, and also what hash ranges have been assigned to the nodes, distributing that information is the only thing that limits really the scalability of this design, because that is a distributed consensus problem, which generally can't be solved for, let's say, billions of nodes. Getting billions of nodes to all agree about what the common set of values are would be very difficult. Okay, so that's the basic view we have of distributed databases, distributed NoSQL databases with a distributed hash table design. There's no bottlenecks, like I said. Both the throughput and the capacity of the system increase when you add more nodes. Why does capacity increase? Very simple. Each node brings some storage capacity, and it can take over a chunk of the hash range so that other nodes can have less data assigned to them out of the total fraction, right? So they can, as you add more nodes, they can continue to roughly evenly share the data. Why is throughput increased? Well, every read or write just goes to the node that is assigned to that particular data. So as you add more nodes, each node can handle reads and writes separately, independently, without involving all the others. So every write goes to just one node, every read goes to just one node, the assigned node based on the hashing. And that means as you add more nodes, you can handle more throughput. Okay, so this can scale to thousands of nodes, and in fact it does. Yeah. So when you think of any kind of big cloud-based storage system, like whether it's Google Drive or iCloud, or the data that's stored that Netflix stores for all their video files, all that data is probably stored in some kind of distributed hash table. Okay, but so we got good capacity and throughput with this kind of design, but what about reliability? I want you to stop and think about reliability. What kind of problems might exist for reliability, whether we have come to a design that is better or worse than the relational database in terms of reliability. So please think about that for a minute. Pause the video. Okay, so what you probably have noticed is that if any node fails, it is sort of a single point of failure for the data that's on that node. So node 3, for example, if that fails or is temporarily unavailable, all the data that hashes to this range that's handled by node 3 is going to be unavailable. Now, the data that's on the other nodes is available during that time. So the system is kind of partially available if one of these nodes fails, but it's also partially failed, which is bad. And if you think about it, if we have a system that has thousands of nodes sharing the data, at any given time, it's very likely that one or more of those nodes has failed for whatever reason. Okay, if we only had one node, then the chance of failure might only be, a few days over a 5-year period when the machine is being used, which is not great, but it's not terrible. On the other hand, if you have 1,000 nodes all running, the likelihood is that one or two of them maybe would be failed on a given day, every day. So every day you'd have some failure, which is not good. All right, so if we want to make this more robust, I guess the natural way of approaching this is to just replicate data so that when there is a failure, you have another node available that has that same data. Okay. So to do replication with a distributed hash table, the simplest way to think about it is, well, you have for every piece of data, you want to store it in not just one location, but you want to store it in multiple locations. In practice, it's nice to store it in 3 locations. We'll see why later on. So this design shows that each data is stored in 3 locations. And I'm using colors, these kind of colored arcs to indicate where the data is stored. So for example, node 0 was it previously the only location for the data in this range here, 0 to 3F, FFFF. But now we're going to store that data in that range on both node 0 as well as node 1 and 2. So we'll take the two numbers, the two nodes afterwards or to the right as we go clockwise in this ring, and we'll store the data. Any data that is stored primarily, was previously just stored in this one location, will also be stored in the two neighboring locations in one direction around the circle, right? So now every node is responsible for a much bigger range of a 3 times bigger range of the hash values. And they each store the same amount of data. They each store now 3/4 of the data, right? Because there are 4 chunks and there are 4 nodes, and there's a replication level of 3. That's what the 3 in the denominator comes from the replication level of 3. The 4 in the numerator comes from the number of nodes in the system. So they each store 3/4 of the total. And this is just one design. Other ways you can assign multiple nodes to each data value, but I think this is the simplest, so let's just go with that. Okay. We still have a hash range, and we're still assigning one primary location to each quarter of the range, but then we take the next 2 and make those also responsible for storing that data. Okay. All right. So when we do that now, data is not just in one place, but in 3 places. That's good for fault tolerance, right? Because if one of these machines fails, the data is available, all the data is available somewhere else. If 2 nodes fail, we also still have the data available, which is why one of the reasons it was nice to have 3 replicas instead of just 2. But we have some consistency problems now once we try to replicate. So replication was necessary. It provides benefits. It allows the system to scale to big size without having always something that's failed. But it creates consistency problems. We'll see why in a couple slides here, and we'll spend a lot of time working on consistency. Basically this whole lecture, because it's actually tricky to get right. All right, but in this class, we're kind of going to be treating this at a pretty high level, not go into the details, but I want you to at least understand why distributed databases have different kinds of consistency policies. And as a programmer, you actually sometimes have to, if you're using one of these distributed databases, you have to actually understand these consistency issues, at least at a basic level. And you usually often you have to make a choice between like what type of consistency you're going to be using. All right, so that's why we're covering this. It's pretty important. It's not just theoretical. Okay, so here's an example where there are consistency problems, and we'll kind of see what consistency means as we go through this example. So we have an update. We're storing a new value, x equals 2. So x is the key, 2 is the value. And because there's replication, this data has to go to 3 replicas. I'm showing just the 3 replicas, not just, imagine the whole system might have more nodes, but I'm just showing the 3 replicas that are responsible for that key. Okay. So while I'm doing this right, you have to keep in mind with a distributed system, you can't make something happen simultaneously on the different parts of the system, right? Because these machines are physically separated. They're all running their own operating systems. They have different competing processes running. So you never know exactly when the message is going to arrive over the network, and you never know when the operating system is going to decide that to run the process that handles that message, right? So I'm showing the arrows of different length and to indicate that like first the message arrives on this first node, but then later on it's going to arrive on these other nodes. Okay, and this is unpredictable. We don't know the person doing the write, the machine doing the write doesn't know which is going to receive the message first. Okay, of course it has to arrive first somewhere. It can't arrive everywhere at the same time because of the randomness of the delivery and handling. So this picture shows it arriving first on the first node. The problem is that at that point, right, once the write, we have a partial write, right? We have x equals 2 written on this first node, but we don't have anything written on these other nodes. And let's say that x previously was stored to had a value of 1 that was written, right? So at this point, we have inconsistency in the sense that the database, in the 3 replicas that are responsible for x, is storing 2 different values, right? In one place, it's storing 2, and in 2 other places, it's storing 1. That's a problem because we could maybe query that data, right? We might want to fetch the data, and we don't know when we're fetching data, what messages might be in flight to arrive at databases, what's going on in other parts of the system. So some client might be requesting data, and depending on who it asks now, it'll get a different answer, right? And if it asks all 3, it'll get 2, 1, and 1. Okay. So somehow this is the problem, right? We'll see exactly why it's a problem, or we'll come up with policies for stating which kinds of problems we're okay with and which kind of problems we really don't like in a later slide. But this is the inconsistency at a basic level that we're talking about. Okay, so we have to have some way of dealing with this. And at a fundamental level, because of these delays we always get inconsistency or unavailability if there's a possibility of delayed messages. There is a theorem from, I want to say, either the 90s, I think the early 90s, called the CAP theorem, which actually proved this theoretically. For a distributed system, you cannot have consistency, availability, and partition tolerance all at the same time. Okay, so these have slightly weird definitions. So consistency means that when you read, you get the most recent write, or you get an error. So actually, that's not weird, but yeah, consistency means when you do a read, you should get the most recent write. You shouldn't get some out-of-date value, right? That's kind of what we saw last slide in the definition of consistency. With availability, that just means that every time you try to do something, whether it's a read or write, you should be able to do it. All right, so the system should not be down or unavailable. And finally, partition tolerance. This is the weirdest one because it really, I think they made it into partition tolerance because it makes it a nice acronym. Or maybe that's just the way they thought about it. But anyway, partition tolerance means that the system can be split, meaning that messages sent from one side of the system don't reach the other side of the system, at least temporarily. right? So partition tolerance means that we allow for an arbitrary number of messages to be dropped or delayed. And what this means, basically, this last bullet point, this last requirement is what makes it a real distributed system, basically. If you're deploying your system and you're assuming that messages are always going to arrive, then you're not designing a system that can be deployed on a real network, because real networks are unreliable. Okay, and machines are unreliable. Machines stop working temporarily. You know, if the software crashes or the hardware crashes, that's another kind of partitioning that happens. If the machine crashes and has to be rebooted, those are both realities that you have to prepare for in distributed systems: machines crashing and the network going down, or at least parts of the network going down. If you assume that the nodes can all talk to each other, and also that they can talk to each other instantly without any kind of delay, you're not really talking about a realistic distributed system. Okay. All right. So this theorem says that if you have a realistic distributed system, you can either have consistency or availability. Right? Either your system can be consistent, and there's a possibility that sometimes you have to wait. And basically what you're waiting for is for the nodes to resynchronize. Or you have to somehow build a system where the network's 100% reliable, and there's no delay in the network, and the machines are 100% reliable. Okay, so this points to a trade-off between consistency and availability, and we'll be exploring that. And by availability, you can think about that as delays, because this, you either have to accept inconsistent data, or you have to accept that you're going to have to wait sometimes to get to get consistent data. Okay, so we have a trade-off between consistency and delay with the CAP theorem. It's not, and it's actually, if you think about it for a little while, you can probably, this shouldn't be surprising. I'm not going to go through the proof, and I don't remember the proof, but I don't know if I've read the proof. But anyway, it doesn't feel that surprising. All right. So we want consistency. Inconsistency can cause weird bugs that we don't want in a code. So as a programmer, we generally want the systems we interact with to behave correctly. Otherwise, it makes our lives difficult as programmers. So usually we're going to be allowing some kind of delay in exchange for having consistency. In this lecture, we'll talk about the ways in which we allow delays to get consistency. Now, if you really need both consistency and timeliness, like no delays, then you do have an option, a reasonable option, which is, remember the option I said was to not have partition tolerance, which I described as not having a realistic distributed system. Well, one way you can do that is by using a centralized database. So if you're using a SQL relational database, then you can achieve both consistency and timeliness. Like, you won't have delays. There won't be times when the system when your requests are delayed for long amounts of time, and there won't be cases when you do like a write and then read and you get an old value. That's possible because it's all kind of in one place. There maybe are some subtleties where you might be waiting because the internal implementation of that centralized database has different threads and disks and stuff that are working in parallel, so it's kind of like a distributed system, but the delays there are pretty limited. All right, so distributed NoSQL database designs. There are many different designs, many different like brands of and types of NoSQL databases. They give slightly different options for handling this consistency and delay trade-off. We're going to look at some examples where we have a client connecting to a database cluster. So this is a client-centric view of consistency, technically, but it's, I think, the most important and simplest to understand. Now, I want you to stop and think about what kinds of consistency properties we might want to ensure. So we have a client connecting to a database cluster. Given what I've told you, what are the things what do you want to make sure is true for the client doing its reads and writes? Okay, give that a try. All right, so the properties that I have for you are some pretty simple ones related to reads and writes done by that client. So monotonic reads, we'll take these one at a time. So monotonic reads means that if a client reads a certain value, if it later reads the same data x, so if a client reads x and reads x later, the same client reads x again, it should always get the same value or a more recently written value. So it should never get an older value the second time it does a read compared to the first time it did a read. Okay? Seems pretty basic, right? But you definitely want that to be true. You don't want to read a value and then later read an older version of that value. That would it would be hard to write a program using that database that worked correctly. Similarly, so along the same lines, if a client writes a certain value to x and then later reads x, we would expect that client to get back that value that it wrote or to get a more recent value. Now, this more recently written value could be a value that another client wrote, because remember, this is a distributed system. There are going to be many clients. It's okay if I write a value. It's okay if I write a value and someone else writes a value, and then I do a read and I get that other person's value, as long as that other write was after my write. Okay? And same thing with the reads. When I read a value and later read a value, I expect to get the same value unless another client wrote a value, or I wrote a value after my first read. All right, and finally, those two are kind of sufficient in some sense. Another one that is actually slightly different is called monotonic writes. This is if a client writes twice to a certain value, certain key. The first write must happen before the second. Okay, so if you do two writes and you do them in a certain order, you want the first one to happen before the second. You don't want it to be reordered. We'll come to that later on, why it's not totally necessary compared to the but the first two are definitely important, and you could probably see how, based on the design based on replication and clients making requests to a distributed database, how that might go wrong. So I want you to stop and think a little for a second about how monotonic reads or monotonic writes could fail if you designed your database poorly, if you designed your distributed database poorly. Okay, try that. We can continue that discussion here, but looking specifically at reads. So just to illustrate it, we have a client that is planning to do two reads. Remember, we want the later read to get the same value or a more recently written value. How could this fail? So given that we have a distributed database, we have two reads, how could this property fail? Like, in other words, the second read gets an older value than the first read. Okay, stop and think about that. Now, if you haven't gotten it so far, I'll give you a little hint. What happens if the reads go to different nodes? Now think, how is it possible for the second one to get an older value than the first one? Even though I executed the first one first, I later do another read, and somehow I get an older value than I got the first time. If I'm sending them to different nodes, how is that possible? Now, again, still, if you haven't gotten it, what happens if there's a write that's happening to that value at roughly the same time? And this write is being done, let's say, by another client. Okay, so the way this works, or at least one example, is that there's a write at roughly the same time, right? And the write happens to be, that data has to go to all three replicas. It's going to arrive at one of them first. So let's say the first step number one, the write arrives at the first node. And then step number two is that the first read happens on that first node. And so that happened after the write, so it's going to get the new value. So the first write gets a new value. This new value, x equals 1, that was just written. But then if very quickly I do another read, and I do that read to a different node, if I did it to the same node, of course I get the same value, and that would be just fine. But I do it to a different node, and I just happen to choose a node that's lagging behind, right? This write didn't reach the third node yet. So this is still storing an old value, maybe x equals 0, right? So the second read is going to get an older value, okay? So we have a distributed database. We built in replication because we don't want to lose data. We have hashing to figure out that these are the three nodes that have the replicas of this data x. We've done a lot of things correctly and intelligently, but we made some mistakes here in the design. So how would you prevent this? Because we violated a simple monotonic read property. I want you to think for a second about how to prevent this problem now by changing some aspect of the system. Okay, so you might come up with a variety of solutions. So one solution might be to force the client to always connect to the same node, right? If this client always connects to this first node, it's not possible for, even if there's a write, regardless of what writes are happening, this node will either get that new get a write or not, and yeah. I guess maybe that depends on how you define the age of the writes, because now that I think about it, maybe you could have a write that was considered older or newer. But if the age of the write is defined in terms of the time that it arrives on this node, then you definitely cannot get data that arrived at this node earlier the second time, because you'll be getting the same value or a later value, a value that later arrived here. Another approach is to delay the second request. So this GET request, somehow this second GET request was too fast, right? Because if I waited long enough, of course, eventually this write would have completed across all these nodes, but I didn't. I went very quickly, and this timing was essential to get this problem. So if somehow I delayed the second request, I could make this work. Now, how we delay it, we'll talk about later. And it turns out the second approach is better than the first one. So my confusion about the first one is not really too important because we're not going to be doing it anyway, connecting to the same node. In general, we're going to have some strategy for delaying requests until there's some level of consistency. Okay. So now let's look at another property, right? The read your writes. This is one that's pretty maybe the most basic consistency thing, the easiest one to understand. If you write a value to the key x later on, if the same client reads x, it should get the same value that it wrote, or it should get a more recently written value. Okay? All right, so the two things I'm doing are going to be putting a value x equals 1 and then getting x. This is all happening in the same client. So how can that go wrong? It can go wrong in a similar way. In this case, I'm showing that I'm writing to one node, and that node, like this database is designed to do replication kind of internally between the nodes. So this node is then responsible for copying the data to the other two replicas. In the previous slide, I showed the writes going out from a client, but there's no real difference in theory from writing to one node and then having that node propagate the results. Anyway, that propagation of the write was slow, or it wasn't. Maybe if it wasn't slow, let's just say that this GET request came in really quickly to the third node before it received the new write. So this GET, if it went to a different node, got an old version of the data. And again, we can fix this problem by either going back to the same node always. Reader writes will definitely be fixed if you go to the same node every time. Or we can somehow slow down the second request until after we've achieved consistency of the write. Okay, so again, we'll come to how we do that later on. So the third property, monotonic writes, can also fail, and we can use the same basic diagram to analyze this. So this property that we're trying to avoid failing is that we want a client, when it writes twice to a certain key, we want the first write to happen before the second. So it's writing x equals 1, it's writing x equals 2. We want the x equals 1 to be written before the x equals 2. The reason we want to enforce this is because later on, if someone's doing reads on any of these nodes, we want them to see the changes in the same order that they were created, right? So I guess it's a reasonable request, but the problems can occur in the same kind of way where you do a write up here to one node and it's propagated downward, but before the write is propagated down here, we do a write, okay? And so we're actually writing the value 2 to this third node before we're writing the value 1. Does this matter? I want you to stop and think about that. I mean, because in the end, is that going to cause inconsistency in the end, or are there intermediate problems? Think about that for a second. In the slide, I say it doesn't matter if the writes are cumulative. In other words, it does matter if the writes are cumulative. So if this write was like not a setting, like these are idempotent operations, like setting a value to a certain constant, doesn't, like this, the second one overrides the first one. But if they were kind of incremental, like if they were cumulative, like if you were doing x plus plus somehow as a write, then I guess the end result would be the same. But if depending on the operation, it could be different. But more importantly, I guess if you're, maybe I missed this point here in the slide, but if you were reading during this time period, there could be a problem. So the reason we have this property is really to protect clients who might be reading from this third node, and they might see the second value before the first one. But that would also be a violation of the monotonic reads property. So I guess I'm saying, so this property seems to be redundant with monotonic reads and read after write, unless you have cumulative write operations that have to execute in the right order to get the same result. Okay, so notice that you can timestamp the operations in a distributed database to prevent this old write from actually overwriting the new one. So this delayed replication of the first write, when it reaches the third node, can be very easily rejected, because as long as the client is like timestamping these requests with either a sequence number or a time of day, then the database can see, oh, this is an old value, and ignore it. Okay, cool. And we can solve this in the same way as before, either always go to the same node or somehow delay the second operation until the first one has achieved some kind of consistency. All right. So we said in the previous slides that we had two basic approaches to getting consistency. The first one was to have the client send all requests to one replica node, and this is attractive because it's simple. One definite disadvantage here is that you're introducing a single point of failure with respect to that one client, right? We know that nodes are going to fail throughout the operation of the system, and when that happens, the client is going to have to switch to another replica. And during that switch, you have vulnerability to the same kinds of consistency problems we had before. So actually, I guess this con is pointing out that it's not really feasible to make the client send all requests to one replica node, because replicas are going to fail. So we can't just rely on this for consistency. Although, that doesn't mean this is totally invalid. MongoDB actually doesn't have replication, so that's also one way to avoid inconsistency. All the data is stored in one node, and so it has, in the CAP, from the CAP theorem, it has C and P. It has consistency and partition tolerance, but it lacks availability. So so for example, if you're trying to access data that's on a node that just went down, and you're using Mongo, then that node, you'll have to wait until that node is rebuilt. Okay, that's the design choice they made. The benefit of that is that consistency is not a problem in MongoDB. So if someone else is doing a write, if there are lots of writes and reads happening throughout a big system, those are all, for a given piece of data, it's all happening on one node. So there's so they're all going to be like ordered correctly. It's very easy to order them on that one node and to ensure consistency of everyone who's operating on it. Because no one is seeing everyone has the same view of that data, because they all have the view from that one node. Okay. The second basic approach to consistency was waiting. So we make the client wait until the whole system is synchronized. And this applies to both reads and writes. Okay. It'll take a little while to explain what we mean by synchronize and what kind of waiting we're talking about. But this is actually the general approach that works well for achieving consistency. Of course, waiting by definition introduces delay. So in terms of the CAP theorem, we are giving up availability, some form of availability. We're doing a trade-off between the availability and consistency. If we want consistency, like basically what I'm doing here is restating the fact that the CAP theorem says that if I want consistency, I have to give up availability, which is to say I have to delay. We'll talk about the specific ways of delaying in the next few slides. Notice that if we're waiting for the system to be synchronized, we're not waiting for the whole system to be synchronized, like all the data across all the nodes to be synchronized. All we care about is the given piece of data that we're working on at the moment. So if we're querying a single key, at a time. The replicas of that key for that one key have to have consistent data before we proceed. Okay, so it's just a small subset of the system has to be synchronized. All right, so we have to have some strategy to figure out when this value is synchronized. And you can stop and think about that. How do we know when the value is synchronized? Meaning when we're writing that all the replicas have the correct value, or when we're reading that we've waited until all those replicas have received the same value if there's an update going on. Well, the simplest approach you might think of is to have both the reads and writes happen on all the nodes and to somehow wait until they all have the same values. So for monotonic reads, if we have remember, monotonic read is where we're doing a read and we're doing another read. We want the second one to get the same value or to get a more recent value. If we make the first one, actually make the request to all three of the nodes instead of just to one. So we get the data and we somehow wait until all three give the same value and maybe keep making requests. And once they all have the same value, then we can say that we proceed to the next one and then do the same. This is not a complete solution because in general, you never know. You can't guarantee that they're all going to have the same value at any given time. They could be changing over time. And then we can also we can make the writes go to all three nodes and wait for all the nodes to acknowledge before proceeding. Okay. So in this case, the second read, the second get, won't happen. The client won't finish this first get until all three of the nodes give back a value and specifically give back probably the same value. Then we'll move on to the next one. So it won't be able to complete this read until this write finishes. That's one way of looking at this. So applying the same strategy to fix read or writes is pretty, maybe even easier to understand. We have the client, doing a write, and it sends that write to all three nodes, and it doesn't consider this write to be finished, this put to be finished, until all three acknowledge the data has been written. So if it has waited that long, if it makes this put block until all the writes are acknowledged on all three, then any later read will definitely not get the older value, right? Because we already know that the newer value has been written. Cool. So that's a general approach. So write in multiple places or write everywhere. But it's we actually can have some flexibility here by trading off how many of the nodes we access for reads and writes. If we write to all of them, we don't necessarily need to read from all of them. And if we read from all of them, we don't need to write from all of them, actually. And so quorums is the term for deciding how many replica nodes you need to involve in the reads and writes for a distributed database. Okay, so in general parlance, a quorum is a minimum percentage of a committee needed to act. So that same concept applies to databases by specifying the minimum percentage of replicas that are needed to do a read or write. Okay, so if we're using quorums, so this is a generalization of what I showed in the previous slide. The previous slide was showing that we required all nodes to acknowledge writes and all nodes to acknowledge reads. So it's actually not even an option here because it's overly costly. But in any case, you're preventing progress until you get the required number of replicas to have a certain degree of consistency. So as an example, the first example here is having a write quorum of all and a read quorum of 1. So this means that when we write to all the nodes, and when we read, we only read from one of the nodes. So that still achieves consistency. If we look back in the previous example, with this read or write problem, we actually didn't need to read from all three if we wrote to all three. Right? If we write to all three, we actually can only read from, we can choose to read from any one of these and we'll still get a correct, consistent value. Right? Or similarly, if we write to just one of them, and if we proceed after writing to one of them and then let the other two be delayed, right? So that's a write quorum of 1. But we read from all three, then the reads portion will actually cause us to delay until all three get the same data. Or if we just get data from all three and look at the one that has the newest timestamp and use that one, we'll achieve consistency. Okay. So those are the two extremes here are writing to all and reading from one, or writing to one and reading from all. And you can see you get different levels of performance for those two, depending on for the reads and the writes. Like in the whichever quorum is all is going to be slower. So if we're writing to all and reading from one, reads are fast, but writes are slow. So if you have a system that has a lot of writes, but few reads, then you could use the other option, which is to write to all, make the reads slow. Sorry, read from all, make the reads slow, but make the writes fast. Just write to one. And then in between, we have this other option, which is a trade-off, which is to require a majority quorum for the writes and a majority quorum for reads. So 2 out of 3 have to acknowledge the write before we proceed, and 2 out of 3 have to we have to get data from 2 out of 3 when we read to proceed. Okay. All right. So as an example here, we can look at majority read, majority write. This is the most complex one, I guess. So, and it provides a balanced trade-off of read and write performance. So if we want to write a value x equals 1, the client would send write requests to all 3. It would wait for an acknowledgement from 2 before it proceeds. So at this point, we know at least 2 of them have gotten the new data. The third one might not have received it. Later on, if it wants to read, so again, this is the read after write example. If any client reads, including the same one, it sends 3 read requests. So if a client wants to read, it sends 3 read requests to all 3. But it has to wait for 2 of them to come back because it waits for a majority. Now at this point, because we're not using all quorum on write, we're not waiting for all of the writes to be acknowledged. It's possible when we do this read after the write that one of the replicas has old data. But we know that because we waited for a majority, that no more than one has old data. So if no more than one has old data, if we get 2 responses back, no matter which 2 we get back, we know that at least one of them is the new data. And if they have timestamps, then we can compare the timestamps to figure out which has the newest data, which is the newest data. So doing this read after write will get us consistent results, even though we only waited for 2 responses for both the write and the read. Okay. Cool. The other example, which I think is a little simpler, is single read unanimous write. So this is writing all, reading 1. So this is again showing the read after write client. We want the client to read their own writes. First, the client writes, in this case, has to wait for all 3 to acknowledge. And at that point, when the client reads, it still is going to send the read request to all 3 replicas. It does that for performance reasons. At least from the client perspective, it doesn't know which of the replicas is going to respond fastest. So if we want the client to be really fast, we send a request to all the replicas, and as soon as any one of them comes back, we proceed. and then we ignore the other 2 that arrive late. Okay, but we know that all of those 3 replicas that responded have already received my write, right? Because of the semantics of the write. The fact that the policy for write was that we waited for all 3 to acknowledge. And in this case, notice that the writes are kind of slow. The time it takes to do a write is the maximum of the latency of the 3 replicas, but reads are fast because it's the minimum of the latency of the 3. So whenever any one of them comes back, we proceed. Right? All right, so that ensures consistency, irrespective of what the timing was of reads and writes that are happening concurrently in the system. What happens if one of these replicas fails? Okay, so I'm going to use the example of a quorum of 2 of 3, so majority quorum, for both reads and writes. And the example here has a client performing a write, and this is like a worst case example in terms of failures. We do a write, we get 2 acknowledgments, and we proceed. But so we have two of the nodes have the new value, one of them has the old value. But one of these new replicas fails. Okay, if the old one failed, that is not so much of a problem because the replicas left both have the newest value. Okay, but this node with one of the new values fails. Now I want to ask you: can reads and writes proceed during this failure time if only these 2 are remaining? Reads and writes to the value of x. Can we read to x? Can we write to x? Even though one of these nodes that stores the new value has failed. Okay, think about that for a second. So the answer is yes. For writes, it's kind of simple. There's no real reason that writes couldn't happen. Even though we have an older value here that's being stored, there's no reason we can't write a newer value over top of it, although that does violate the monotonic writes property. But if we cared exclusively about monotonic reads and read after write, then we could write here and we also could read. When we read, we'll send requests to all 3. Now this failed one won't respond, but we'll get a response from these 2. Now we get 2 different responses, and the client has to choose between them. Now if the client didn't have a timestamp on each one of them, then it couldn't really make a choice. But since there is a timestamp, then you can just choose the most recent one. And also notice that when a replacement eventually joins to replace the old failed replica, it'll request all the data that should be assigned to it from the replicas, and it'll get this write that any writes that occurred previously will be accepted by this new node. All right. Another failure scenario here is I'm using a different quorum strategy here. If I have a write quorum of 3 and a read quorum of 1, and I have the same failure, so I'm writing to all 3, one of them fails before the new write arrives. Now I want to ask you, can reads and writes proceed? Even though we only have 2 nodes with the data and 2 nodes available out of 3 replicas, can reads and writes proceed? Well, actually, it's a mixed answer, right? We can't write because if we're remember the policy for writes in this case was a unanimous quorum. All 3 have to acknowledge the write, but one of them has failed, so we're not going to be able to get acknowledgments from 3. So if we try to write at this point, the system is going to be stalled. We're going to have to wait for this node to come back online. So the system is stalled until this node is replaced, but reads can proceed because reads only have to get an acknowledgement from one of the nodes. Notice that if we had a quorum, an all or unanimous quorum for both reads and writes, which we don't need, but if we had that, then reads also would not be able to proceed because the reads would require a response from all 3. But there's no real need for that, so we wouldn't implement it that way. So with both of these strategies, when there's a failure, there can be a delay for doing reads or writes, but data is not lost. We still have, we do have fault tolerance. We can bring the system back online, but there can be a temporary delay in accessing either for read or write certain parts of the key set. Okay, this new replica can join and it can request data, and then after this new replica has joined, regardless of whether it's received the replicas of data, it can start accepting writes on all three. Okay. So you may be wondering, looking at these examples, why this is scalable, because we've been doing the writes or the reads on like all three of the nodes. But remember, that was just really an illustration. In a real system, we're going to have lots of nodes, like n nodes, a huge number. It could be thousands, hundreds, or 10, whatever. And we have a replication level of we have replication of data, so that the data is not just in one place, but that replication level is a constant level, usually 3. So we have data in 3 places, maybe 5 places, I don't know. More than one place, maybe 2 places. That's also possible if you want to save some space. If you replicate data in 3 places, so every given every key is stored in 3 places. So if you do a write to the value the key z, that goes to, let's say, these 3, and reads of 3 go to of z go to these 3 nodes. But other operations on different keys will go to different sets of 3 nodes. So the system is scalable. As you add more nodes, you get more capacity. Every write or read is going to involve at most 3 nodes. So it's still a constant number. It's not 1, but it's a constant number. So don't let those previous illustrations fool you where I was showing all the nodes being involved. I was just showing the replicas that are involved in that particular operation in those diagrams. In reality, you should have a picture like this in mind. Okay. And in the quorum policy, when I say a unanimous quorum or you're writing to all the nodes, what I'm talking about is writing to all the replicas, and that number of those replicas is going to be like 3, so it's going to be a small number. So we're not writing to all the nodes, just to all the replicas. So at this point, I want to ask you, why did we choose 3 replicas? Can we choose 2? Can we choose more than 3, like 4 or 5? And what are the benefits of doing that? So think about that for a second, or a minute. So yeah. Basically, by having more replicas, we get more fault tolerance before we lose data, and more fault tolerance before we have to delay requests. Like if we had 5 replicas and 1 node failed, and we were using a majority quorum, then regardless of which 3, if I make requests to 5, there's no way... there's no way to get 3 responses that don't have the newest data. I guess that's not... I think... Oh, sorry. The reason is mainly to do with fault tolerance. So if a node fails, having 3 replicas means 2 nodes can fail without losing data. If you only have 2 replicas, then only 1 node can fail before you lose data. If you have 5 replicas, then 2 nodes, like I said, 2 nodes can fail before the system is offline. 4 nodes can fail before you lose data. But yeah, with 3 replicas, if 2 nodes fail, then the system is stalled because you can never get a majority of 2 out of 3 for all the data. But with 5 replicas, 2 nodes could fail, and you would still be able to get a majority, and the system would be able to proceed. Okay, so you have both more fault tolerance before losing data, and more fault tolerance before the system is offline without losing data. Or so let's say before the system is stalled temporarily, like delayed, before requests are delayed. Cool. Okay. So in this lecture, we looked at ways of talking about consistency that were like monotonic reads, monotonic writes, and read after write. There's another way of looking at consistency that generalizes those, or like includes all 3 of those properties, which is called linearizability. So all of those things, all those consistency properties I mentioned before, fit together are covered by linearizability, a single concept. And this is a stronger form of consistency because it includes all three of those in addition to some other concepts. And it's also pretty easy to understand. So if it might be easier for you to just remember this one definition of consistency than those three, but this is actually stronger than the other three. So some different systems will have different levels of consistency. Anyway, sorry. The linearizability means that the partial ordering of distributed actions is preserved. Partial ordering. Okay. Why is there a partial ordering? Well, we have distributed actors. It's a distributed system. We have clients all over the place. We have database nodes all over the place. Each one of those actors has observations and has actions. So it does certain things. Like, for example, if we have Anita and Sam, Anita does A, B, and C, and she knows what order she did those things. She did A, then she did B, then she did C. Sam does S, T, and U, and Sam knows that he did the things in that order. That is a partial ordering. When these actions are put into a distributed system, they're joined together, and they're propagated in different orders to different parts of the system. But at any given point, you should be able to, when you observe at any point in the system, you have a linear, you have a final ordering of these two, a serialization of these two, I should say, and all other actions in the system that form a series of observations at any point. So we have to somehow order these A, B, and C and STU have an effect at every part of the system. They might be interleaved differently. Like it could be A, B, C, like at the bottom I'm showing, it could be A, B, C, and then STU is what is observed at some point. Or it could be S, A, B, T, U, C. This is where I'm taking Sam's first thing, and then Anita's first thing, and then then Anita's second thing, and then Sam's second and third thing, and then Anita's third thing. That's another serialization where those events arrive in kind of like interleaved order. And then finally, it could be that all of Sam's stuff arrives first, and then all of Anita's stuff arrives. All of these are okay. All of these are consistent with the partial ordering. Like if you were to show these observations to Anita, she would say, okay, these are all reasonable because I know I did A, then I did B, then I did C, and these observations have those things in that order. And this A, B, and C, these letters represent probably reads and writes in a database. But this theory applies to not just databases, but any kind of distributed system. And then similarly, Sam sees his things in the right order. Now, the distributed system would not be linearizable and would fail this test if somehow there was an observation serialization that broke these partial ordering. So if B appeared before A in any of the observations across the whole system, if it was possible for an observer in this distributed system to see B before A anywhere, then that would be inconsistent under the linearizability definition of consistency. Okay. Yeah. So that's pretty long-winded, but like it's a pretty simple concept. We have things happening all over the place. We have those events just propagating in different orders because the system is big and separated in time and space. But all those actions originate in one place, and the observer in that place knows what the partial ordering is of the system in terms of the things that started in their location. And that partial ordering should be preserved in all of the serializations. These serializations are going to be different in different parts of the system because the events arrive in different orders. They propagate through the system differently depending on where they started, but they all should obey the partial ordering that's defined at the origins. Cool. That's called linearizability. And so consistency is a pretty complex topic, and there are many different definitions of consistency. So I just mentioned linearizability. That actually includes writes follow reads, monotonic reads, and monotonic writes. So I mentioned these three, and I mentioned linearizability. So linearizability requires, or like, if you have linearizability, then you also will have monotonic reads, monotonic writes, writes follow reads, and read your writes is the one that I talked about in this class. It's kind of similar to writes follow reads. well, no, it's not. Reader writes is one I talked about. But there are other forms of consistency that are defined, and different systems can implement different forms of consistency. Yeah. So when I say linearizability is a definition of consistency, it's not the only one, but it's one that's easy to reason about, both for the person developing the database and also for the programmer using the database, more importantly. So generally, you want all three of these things, and you also want linearizability in your database. If you want to learn more about this topic, it's pretty interesting, in my opinion, because it combines CS theory and sort of mathematical proofs with real system design. So these are issues that really come up in distributed databases, in which are the fundamental building blocks of high-scale systems. You can't build, a YouTube without some kind of distributed database. Anyway, so this is covered in much more detail. This one lecture is kind of expanded into many in distributed systems class here, CS 345. And there's also, if you want to just learn more about it without taking the class, you could check out Chapter 7 of the distributed systems book that I recommended, or Chapter 9 of the Designing Data-Intensive Applications book. Okay. I talked about distributed hash tables today and kind of kept saying that these were used in NoSQL databases. So examples of NoSQL databases are DynamoDB, Cassandra, Elasticsearch, which you use in the homeworks, and MongoDB. But distributed hash tables are also used in distributed file systems. There's not really too much difference between a NoSQL database key value store and a distributed file system, because you can consider the file name or path plus file name to be the key for the data, and the file contents to be the data. And so examples of distributed file systems that use something like a distributed hash table are Hadoop HDFS, Google File System, which includes a couple different iterations called Colossus and Bigtable, and also Amazon S3, which you can use on AWS. All right, so to recap this lecture, we talked about distributed database consistency. Started off by pointing out that when we replicate data, we need to replicate data to prevent a single failure from losing data and a single failure from creating downtime. But when we replicate data, we have consistency problems. And also notice that the more nodes you have, the bigger your system gets, the more likely a failure is going to be. So we really do need to have replication. There's a theoretical trade-off between consistency, availability, and partition tolerance, which is in the CAP theorem. You can only have two of them. Generally, we don't have partition tolerance. We can't guarantee partition. We can't avoid partitioning in a real system. So we have to have partition tolerance in a distributed system, which means that we're left to choose between consistency and availability, generally, in real systems. MongoDB chooses consistency. Really, every database chooses consistency, and the way they do that is by introducing delays in the way requests are made, using different quorum levels for reads and writes. I also, what's interesting here is also, that's the reason why I mentioned the details of different quorum levels, like, writing to all, reading from one, write majority, read majority, is because in some databases like Cassandra, the programmer can actually choose on a per request basis. Like for every read or write, you can choose the quorum level for that read and write. So you can actually make this trade-off between whether the reads are delayed or the writes delayed. You can make that at a very fine-grained level. And so as a programmer, you have to be aware of that. Even if you're not building a distributed database, which I assume you're not, you have to understand what's going on behind the scenes at some level. Okay. I mentioned different, like the definitions of consistency in terms of monotonic reads, monotonic writes, and reader writes. Altogether, these are covered by linearizability, which is where the partial ordering of actions is preserved. Yep. So that's about it.